Panel on Moon, Mars, or asteroids, where do we go first for resources? We have a spectacular panel. Unfortunately, Pete Worden is ill. He sends his regrets. We asked Esther Dyson, who graciously consented to serve as moderator tonight. Esther's the lovely lady sitting at the far end of the table from me. I'd like to introduce our panelists. The first is Professor Micah Hearn, the University of Maryland, a great asteroid prospector. Next is Greg Baiden, the world's leading practitioner of automated mining on Earth so far. Hopefully that will change. Mark Sonter, another experienced mining engineer. Professor John Lewis, whom I think you all should know from his advocacy of non-terrestrial resources for the last 3 to 4 decades. Jeff Greason, CEO of XCOR Aerospace and a recent member of the Augustine Commission on Human Spaceflight Plans. And finally, Dr. Paul Spudis of the Lunar and Planetary Institute, whose instruments were instrumental, if I can say that, in helping verify the presence of water and volatiles on the moon. So I will turn this over to Esther, and thank you all for coming.
Thank you. Great. I just want to describe the panel briefly. Lee Valentine asked me to be here as the time bureaucrat. I'm kind of the opposite of Pete Worden. I know very little about this, so my main role here is to facilitate, to keep time, and to manage the Q&A, and to ask dumb questions that might perhaps elicit smart answers. Each of these gentlemen is going to speak for 5 minutes or less, and that's my first task, to keep them to time. Just like a regular rocket, everything needs to be very well timed. And then they're going to either violently disagree with one another, or if they fail to do that, we'll take your questions. And depending on how that goes, we'll probably end around 8 or 8:15, and then everybody can hang out and have a great time. As I mentioned, I'm not an expert on the topic. I came here to learn, so this is going to certainly help me pay great attention, and I hope all of you will. I think it should be really interesting. And we're going to do it in the order listed here in the program, just to make things simple, which is to start with Jeff.
No pressure.
You get to relax after you've done it.
Beautiful, slack. Okay, let me start by trying to assuage the partisans of all the bodies I'm not going to advocate for. I have no doubt whatsoever that all of the places that we've discussed, Mars, near-Earth objects, and the Moon, to which I would add Phobos and Deimos, because I think they're a fourth interesting class. It's very important for some applications, are all going to be sources of extraterrestrial resources that are going to be very important. But the topic I was asked to address is which one's going to happen first. I think NEOs are very interesting. I think they're very important. But unless you have a government writing all your checks for you, I have tried over the years to make a business case close for doing NEO resource exploitation. It's hard. And the reason it's hard is because of the revisit time. You can't get back to the same asteroid that's energetically favorable for returning materials all that frequently. And in the real world, figuring out how to do resource extraction, even here on Earth, from a given ore body is not a trivial process. So until we have experience, the day will come when we can look at an asteroid spectroscopically and say, that's a type 37A. We're going to use the process we used the last time that we looked at an asteroid like that, and we can send out a mining mission with a reasonable prospect of it working the first time. But that's going to take a long time to get to. The other business model for NEOs that makes sense is sort of the De Beers model, I call it. You go out and plan to do all the return you're ever going to do from a body once. And then since you flooded the market, what you have to do is hang on to your ball of platinum or whatever it is and parcel it out in little snippets over the course of 20 years, hoping that nobody comes and takes it away from you and you maintain clear title and no government decides to nationalize it along the way. So I think it's going to happen. I think it's very important. But I think if you ask the question which one's going to happen first, especially in light of all that's come out in the last 10, 15 years about the moon, which I'm sure my colleague will speak more about, I think the moon is clearly the answer. It's close. It's close enough for teleoperation to be useful. We can get to it with quite predictable frequency. We always know where it is. It's always close. And you know, at this point, you really have to willfully ignore the preponderance of evidence not to believe that volatiles or in extractable economic form are available at the poles. Now, the question then is, what's the market for that? And that's the problem. You know, ice is not actually all that useful unless you have something you want to do with it. But I think the probability is very great that one or more governments around the planet are going to maintain a human space exploration program without necessarily saying which ones that might be. And if you're planning on doing human space exploration, you got to have a lot of propellant. You know, doing a human space program, even on the scale of Apollo, is a 300 tons per year propellant demand, and I think some countries are going to want that. Whether ours is one of them or not is a question for our policymakers. So, and the important thing about extraterrestrial resources is once we start extracting and using anything from anywhere for any purpose, the incremental cost of adding one more kind of resource that we extract and use from various bodies is next to nothing compared to the cost of getting to do it in the first place. So it really is an irreversible tipping point. Once we start figuring out how to make it make money for anything, we can start figuring out how to make it make money for everything. So it's a big deal, and if we were a wise and frugal nation, we would conduct our exploration programs in such a manner as to create a demand for those things, because it would change the universe forever in a good way.
Thank you. Yeah, if you guys want, we can vote at the end. So next is Mike Ahern.
Okay. People hear me? Yeah, I guess that's working. I will argue that, in fact, at least with the current state of the federal government in this country, you probably do want to go to NEOs because that's where NASA wants to send people currently, under the current administration. Jeff has made a good point that it is very hard to go to one more than once. And that is definitely a problem. But if you're doing a pure research, a pure resource extraction program, then you've got to fund it entirely commercially. And by going to somewhere where NASA wants to go, also you can do some mutual piggybacking and come out ahead. It's not hard to go to an NEO. I have a spacecraft that I'm in charge of that's going within 700 kilometers of one on Thursday. It happens to be a very icy one, but it's an NEO, and water is a valuable resource in some circumstances. You know, bringing water and dropping it in the Atlantic Ocean doesn't buy you a whole lot. But if you're on the moon, bringing water might be valuable.
Brevity is the soul of wit. Thank you. I would argue, though, that perhaps NASA says it wants the commercial sector to go to the moon, and so it's not necessarily true that you want to go where NASA wants to go. Maybe you want to go where NASA doesn't want to go. So next is Mark Sonter, please.
I think brevity is going to be the soul of wit here too. What I want to say, I've become increasingly agnostic over the last decade or so as to whether asteroids or Mars or Phobos, Deimos, or the moon will be first. But most of my study and my interest has been looking at the near-Earth asteroids. And there's absolutely no doubt that the number of potential targets there has exploded dramatically from something like 300 known near-Earth asteroids. If you go back to the mid-90s, we now have something like 8,000, 9,000 near-Earth asteroids, and a substantial subset of those are Earth grazing, or at least of low delta V for access and of low delta V for return. There's multiple possible products, as we know. Along with my colleague here, Dr. Lewis, I think that water, and Mike Ahern, I think that water is a potential first product. But economics has to be the driver as to design of the miner and of the entire mission, and economics has to be the driver as to the choice of the actual target. Is the target Phobos or Deimos, or is the target the Moon, or is the target near-Earth asteroids? Economics is what drives choice of mining projects on the Earth, and economics is what will drive choice of projects in space as well. What else is there to say? The potential value of ore, and ore is stuff which you can mine and extract and sell for a profit. The potential value of ore from any of these locations, regolith in a permanently shadowed crater on the Moon, regolith on NEOs or NEAs, or deep matrix material in NEOs or NEAs, the potential value of this stuff, if you can get water out of it, or platinum group metals or nickel iron, the potential value of this stuff, if it's competing with a lift cost from Earth into orbit, is $10,000 per kilogram. And that's extraordinarily high value ore. On Earth, mines generally run at a profit if the value of the ore is 120 or 100 or 130, $150 per tonne. And the sort of stuff we're talking about is of the order of $1 million a tonne. So you can do things, you can be profligate in how you accept poor recoveries. You can do things mining in space that would not be considered feasible on the Earth. But again, we go back all the time. How do you judge the economics? How do you sieve the different potential projects to decide what your target's going to be? And I think I should stop at this point.
Thank you. That was interesting. One question that comes to mind for later is how refining itself is going to be different in a vacuum. And now we move to John Lewis, please.
Sort of interesting to be sitting here with a bunch of people who are represented to you as visionaries. And I would like to say that a visionary is a person who foresees something at least 100 years before it actually happens. And I don't want to be a visionary. But sadly, I'm 40% of the way there. Help. What Mark says about economic drivers is, of course, absolutely central. What we as a community interested in space resources and space manufacturing need to do is to be quick on our feet, be flexible, to have an answer to every question that comes up, be able to respond to any opportunity that opens up. If anybody needs commodity X in location Y, we should have thought out how to do it. Historically, I'm identified with asteroid resources, but if we had a banned federally sponsored program going back to the Moon right now, I'd be right at the head of the line saying, let's go after lunar resources. I desperately want to get past the point where we are completely dependent upon the governmental dog that tends to shake us at the tip of its tail. We need to think in terms, always in terms, of commercializable opportunities. We need to think in terms of customers other than governments. I've been spending a lot of time in China over the last few years. I was a visiting professor at Tsinghua Daxue in Beijing for a year, along with my wife. We're inseparable. And it was very interesting finding out what their perspective on all of these things is, and seeing their interest in helium-3 and in solar power satellites. If you're interested in hearing about that, come to the banquet tomorrow night, and I'll tell you enough to give you indigestion on the subject, and for that reason I'm speaking after dinner. So, so think, if we go to Mars, what Mars resources should we be utilizing? If we go to the Mars system, how do we use Phobos and Deimos resources? If we are going to the moon, if we're going to build an equatorial base or a polar base of the moon, which resources should we exploit to minimize the cost and maximize the effectiveness of that facility? And if we have answers to all of these questions, we'll fit in somewhere. But my crystal ball, I think, is foggy enough so that I'm not confident saying which one it will be.
Okay, thank you. Greg Baiden, Mr. Mining.
Yeah. I want to put this in the context of, I'm in the process right now of designing what's probably going to be the world's next largest mine, and it's in the James Bay lowlands in northern Canada. And it's a nickel, copper, gold, platinum, palladium, silver deposit. And it's so far worth in the order of about 11 or 12 billion dollars. And what we spend all of our time doing is trying to figure out if we can mine it for something less than $11 billion to make a profit, without having most of the ocean flow into the mine, or without digging into the bog there and releasing more mercury than we'd ever want to release. And so as I put it into that context and I sit back and I would say to you, where we're going to go is wherever people want to go, and we're going to mine what people need wherever people want to go. And you know, there was a slogan that went through our mining school when we when I was going through, and it kind of goes like this: if you can't grow it, you got to mine it. And so one of the things that I've spent a lot of time on over the last 4 years is building a strategic plan for how to mine the moon for the Canadian Space Agency. And John came up to see some of the work that we did at INCO, and we're at a point now with teleoperation of mining equipment that I think it's feasible to mine the moon. And one of the things that we have to consider is what's on the moon in enough concentration to mine. Water that can become rocket fuel makes a lot of sense to go to low Earth orbit because there's a marketplace for it. Helium-3 doesn't yet make a lot of sense because we don't have any fusion reactors. The minute we get fusion reactors, helium-3 will well overtake water as what we need because we're running out of energy. So I say all that in the context of if somebody wanted to go to Mars, we're going to figure out what we would have to mine on Mars to support them on Mars, because you can't go there without that kind of material. Now all that said and done, mining the moon's not going to be an easy thing to do. And you know, part of what we came up with was the idea of having to go underground to mine the moon, to protect astronauts and everybody else. That's not a simple undertaking, because as Esther can attest to, she saw an explosive blast the other day, and that explosive blast doesn't work very well in a vacuum. And we're going to have to figure out how to do that kind of thing into the future. But my vote is for the moon, faster than anybody else. And I would argue today that I could easily make a business case for going to the moon, given the background that we have trying to do the business case for this kind of a deposit in the middle of nowhere at minus 40 degrees C with nothing but moose and fox for friends. Anyways, thank you.
That was, and this particular explosion was in the middle of Texas, and very instructive. Dr. Spudis.
A lot of my thunder has been stolen by some of my previous speakers. I'm fairly well known for advocating the moon as the next destination for a variety of reasons. Specifically in regard to resources, I think that the new discoveries about the poles of the moon in the last couple of years have really made the moon a much more attractive target than it ever has been up until now. I always like to start off my talks by saying there's 3 reasons to go to the moon. It's close, it's interesting, and it's useful. Of those, the first and the third, close and useful, I think are the most relevant in terms of resource utilization. Jeff's already alluded to the issue of accessibility and closeness. I envision a lot of the early work in prospecting and demonstration and feasibility testing of resource extraction to be done via remotely operated robotic machines, and there's no reason not to do that. And in fact, I'm actually working on a paper right now that describes an architecture of which the first half of it is entirely robotic. So people effectively go to the moon, they move into a turnkey outpost. Everything is done remotely. And you can do that from the Earth. Because of this 3-second round trip radio time, you can actually do real-time remote control on the moon. It's not possible for most other solar system targets. The other thing about lunar resources that's particularly interesting is that we now know that the water there is free water. It's unbound. It's present in free form. And fundamentally, all you have to do is scoop it up and heat it to 100 C, and you're going to vaporize it. You don't have to break any chemical bonds. You don't have to bake solar wind hydrogen out of the dust. It's there in concentrated form. Now, you've all heard about the L-Cross stuff. That was big news last week. Well, we've actually got a radar mapper. One was on Chandrayaan-1, and one is currently operating on the moon on LRO. We found evidence for effectively nearly pure water ice in over 40 craters at the North Pole and about 30 craters at the South Pole. And it's hard to imagine this stuff being anything but that, but I readily admit it needs to be verified by an on-the-spot measurement. So what this suggests is that mining water on the moon is going to be a lot easier than we thought. At least I grew up thinking about how to bake 100 parts per million of hydrogen out of the regolith, and you have to heat it up to 700 degrees, and what do you do with the dirt? It's an incredibly difficult thing. It looks like it's much easier than that. And one other thing, let me close by this issue about where's the market? What are you going to do with this stuff? I think that the basic answer to that is the market for lunar water is to create a cislunar transportation system. Because if you can do that, if you can build a system that, for example, uses reusable landers, propellant depots, and cislunar that can routinely access the lunar surface, you can access any other point in cislunar, and that's where virtually all of our satellite assets reside, our national security assets, our scientific assets, and our economic assets. So fundamentally, what I envision and what I've been advocating is that we're spending roughly $20 billion a year on a federal space program. I think we ought to get something useful for that. And one thing that is useful would be for NASA to go to the moon, not to do Super Apollo, not to do sorties to all these different spots. As much as I love that, I'm a geologist, I'd love to go tromp around the Aristarchus Plateau for a month. But rather, you go to one spot, you go to the poles, it's the Willie Sutton principle, that's where the money is, and you learn how to extract this stuff, and you begin to export it to space. The first customer is the government, because the government's going to use what you make. But ultimately, that market will expand. It's almost if you have the stuff there available for sale, you will have customers for it. So I'll just stop there.
Great. Yeah. So I'm going to ask, I'm first going to ask the panelists whether anybody, and I'm going to keep holding the mic from now on so you can nab that one. Just if any, this is for me who knows nothing really interesting. My first question, which you may or may not want to answer, is have you ever thought of, at least the title says resources, it doesn't say minerals. Have you ever, and some of us here come from the synthetic biology conference. Have you thought of biological things as being resources, and does that change your answer? And the second is, if anybody wants to either question one of the other panelists or disagree with them or build on it, let's do that first, and then let's do some questions. Everybody believed, no, good, go ahead. This is Greg Baiden.
Yeah, I mean, if from a biology point of view, I've done a lot of work on undersea mining over the last number of years, and a friend of mine, Stephen Scott, and I have been looking at how to help do the undersea mining in Papua New Guinea. But Steve was one of the first geologists to go to the bottom of the ocean. And what he and the other geologists found was quite amazing. And essentially a whole ecosystem based on a chemosynthetic world as opposed to a photosynthetic world. And you know, if I was going to look at it not from a resource point of view in terms of making money, but finding life somewhere, some of the moons around some of the other planets make a hell of a lot more sense to go and find life. And I think that that's going to have a payback for our planet that will be quite tremendous if we could find life within our own solar system. And so on the one hand, well, I come from the world of business. The other hand is I sure would like to find life. And the best place that I can think of right now seems to be some of the moons around Saturn.
Okay. Jeff?
The other two resources that come to mind for me are, there's obviously the energy resources of space that we can harvest. And I think that while the question about whether or not that's going to be ever competitive for baseload power is very much an open one, I think it'd be quite credible to make a business case close for doing energy harvesting for spot power. Now the challenge there is that we need a high power beaming technology that can beam to small spots, which also happens to be just what you need for doing beam power propulsion for exploration missions. Once again, exploration comes into the mix. The other thing, speaking of biology, I mean, as far as we know, there's not an awful lot of biology in the immediately accessible space to get to. But I think that's going to be one of the underappreciated uses of the moon. I think as our biological capabilities get more and more powerful, we need the equivalent of what places like the Mojave Desert used to be, where you can go do experiments that you really don't want to do in your backyard. And the moon is a great big sterilizer. You know, if something goes seriously wrong, you bulldoze the crater and move on to the next one. And we can try things there that we really responsibly might not want to try here, and God knows what we'll get out of that.
Great. Okay. Gentlemen, so I'm going to ask people who have questions to ask their questions and say who they are, and then I'll repeat them unless there's somebody who has a mic they can run around with. And if you're, this is one way to keep questions short, making me repeat them. If you really need to say something long or complicated, you could come up here and borrow my mic. So.
I'm Phil Chapman.
But do you want to stand up and just face, then maybe they have a chance of hearing you. Phil Chapman.
I had a quick question and two comments, and the question was, what's the geological origin of the James Bay deposits? Is that an asteroid impact by any chance?
The origins of the James Bay deposits, was it an asteroid perchance?
I'm not sure we know yet. Sudbury looks like an asteroid deposit, and the James Bay deposit, the way that it's shaped, is all kind of hidden underneath the bog, which can be anywhere from about 3 meters to about 300 meters. But from what I've seen of the shapes, it sure looks like an impact of some description, because it's kind of conical with fracture zones. And but nobody's really explored it to find the other half yet, so we're not quite sure.
Okay, my two comments is, one is that we talk about resources from space, and the usual implicit meaning of that is what can we find in space that is useful to people back here on Earth. And that, in my opinion, is like saying that the only reason we live in Hawaii is to export pineapples back to the mainland. The real takeoff in becoming a real spacefaring species will not happen until the principal customers of people working in space is other people living in space. And we need to think big and get to that point. My second comment is that if you want to it's true that it's hard to get to Neo several times. But the obvious answer to that is to take a mass driver with you and bring the whole thing back so that you can work on it at your leisure.
I want to respond to
Yeah,
those two.
actually, why don't you repeat them, just summarize them so that people know what he said, and then.
I'm going to summarize Bill very briefly. Why don't you just bring the whole asteroid back? That's what I was referring to as the De Beers business model. You know, you go out once and you bring this enormous wad back, but among other things, I think the legal regime is going to have an enormous amount of evolving to do before that's a practical business proposition. And the other one was, you know, isn't the real importance of space resources basically serving the people who are going to live in space? And the answer to that, in my opinion, is, of course, absolutely that's true. But to carry your analogy farther, you know, if Hawaii had not already had an indigenous population and we hadn't been able to grow pineapples and sugar and send them back, you would probably still be waiting for the first people to show up there. The importance of resource extraction and export back to the home society is not that that's the be-all and end-all of what you do, but that once you can do that, you have reached economic escape velocity and you now have surplus wealth that you can reinvest in your local community, and the next thing you know, you have Hong Kong. So it may or may not be a necessary step, but it's a sufficient one. And if we can get there, you know, the stars are ours.
Economic escape velocity, I like that. Greg, and then John.
Just one thing, I will say this to you. In the diamond industry, if you brought back Lunar branded diamonds, they would be worth an awful lot of money.
John.
My way of thinking is that there are really two things that we might consider bringing back to Earth from space. Number one is energy. Number two is precious and strategic metals. But I don't think we're going to bring back an ounce of precious and strategic metals until we have something going on in space that consumes the iron and the nickel and the other things that you're producing in great quantities. I think it is an obvious and lucrative side issue to the processing of material in space for use in space. So think energy and think what those markets might be in space.
Thanks. Okay, good. Now we have lots of questions. So blue shirt at the front table. And if you can stand up, face the rest of the room so they can hear you.
Al Globus.
Great.
San Jose State, actually, here at Ames, doing other stuff. You make the problem that if you bring back the whole asteroid, it's this enormous thing. Well, why not just bring back little asteroids? There's lots of them.
Great. Good comment. Way in the back in the black shirt.
Hi, Ken Murphy. I've got two quick questions. One, do you see the time value of money having an impact on which is the first destination to go to? Second one, I've heard economics and the De Beers model and diamonds. What about the Walmart model? Low margins, huge volumes, as opposed to huge margins and low volumes.
What about the what model?
The Walmart model.
Oh, Walmart.
Walmart, yeah. Like Tesco.
Woolworths, Coles, yes.
Woolworths, yeah.
Walmart. NPV is crucial. Net present value and time cost of money is crucial. And that's one of the things that has me swinging back away from asteroids towards the moon, the more you hear about availability of water on the moon. But if you're going out to an object that you can only get to once and mine once in a single mission situation, then the net present value is dominated by the time of the mission out and back. And what you say is quite true. Now, the Walmart model, I think you mean getting everything from the asteroid, is that what you're saying?
No, mass market.
Mass market.
Economy of scale in mining and processing.
And travel. I mean, whatever it is, do a lot of it.
If you're returning material to a market which is in orbit, you don't need to bring very much mass back before you're getting $1 billion plus return.
In my notes, it's the Bechtel model. I didn't address it because the topic of the panel was kind of what's going to happen first. Yeah, there is a steady state asteroid mining market at some point in the future, whereas you get to the point where you know so much about the population of asteroids that you can design the mission for the next one that's going to come around with reasonable prospects of success, and then it's a lower margin, year in, year out, you make money business. And I see that happening someday, but someday is not anytime very soon. I mean, bear in mind, we haven't returned the first sample from any one of these bodies yet. So given the revisit opportunities and frequency, we got a ways to go before something like that can happen, and I think we can do other things first.
Greg?
I'd like to just say that Walmart model is probably not going to be a viable model, and the reason it's not is it's probably more like the industrial minerals model and or cement model. And the problem with the cement and industrial minerals model is that there's a radius of transportation that goes around them. And if you can't transport that material, if you transport it 1 mile further, you won't make any money on it. And so you have to have stuff of sufficient enough value that you can manage the transportation costs to wherever you're going. And so if you look at the transportation costs that we're looking at, things are going to have to be of huge value to manage those costs.
Yeah, John?
Yeah, just think in terms of an asteroid that has platinum group metals in it. You may only find 10 parts per million of the asteroid worth returning to Earth. But you have to separate it out first. And to separate it out, you have to separate it from, first of all, separate the metals from the silicates, and second, separate the metals from each other. We've talked about, we've tested in the laboratory schemes for doing this. But the market is going to be for that vast quantity of ultra pure iron and nickel that you're producing, not as a byproduct, but as your main product. The platinum group metals are the byproducts, and sure, they're worth bringing back to Earth if you're already making a buck on the iron and nickel. Ultra pure iron should not be underestimated. It has the corrosion resistance of stainless steel, and it makes up about 30% of the asteroid belt.
Great. Okay, so now there's way too many people for me to keep you in order. What I'd like to do is have the guy in the white shirt over there talk. Then the rest of you, if you line up, that way there'll be some sort of order, and if you just come on up here, seriously, that's how it works the best. Then I won't miss you, and the first people, yeah, you can all stand up. But that way I call on people in some proper order, and it's, the only exception to this rule is if one of you has a question that's specific to something that is right on the table right now, then just jump to the front of the line, and if you ask something that's not relevant, the other guys will beat you up. So go ahead.
I'm Will Marshall, and I work on the XCOR science team, and
Yes. Bravo.
And yeah, so lots of water on the moon. So I come at this problem mainly from the perspective of being interested in self-sustainable settlements, okay? And from the perspective of self-sustainable settlements, I think the argument's basically over. I mean, the moon is the most obvious place for self-sustainable settlement in the Earth.
The argument's not over.
Huh? Well, the argument's not over.
You want to get up in line too?
From my perspective, the argument is essentially over, and it's just a matter of time for this stuff to sink in. However, and just to emphasize that, I was doing a back-of-the-envelope calculation based on the water content we found with Aerospace in the. If you extrapolate that to the other permanent shadow craters, even if you make the most conservative assumptions, the number of people that you can sustain there on the moon is about maybe 10,000 for 1,000 years to 10 billion for 1,000 years. Just in terms of the amount of water, there's big error margins on that, but it's sort of 10 million people for 1,000 years, plus or minus a few orders of magnitude. There's large errors because there are still massive uncertainties about how we can extract this stuff. But the point is that it's a hell of a lot of people. And on a NEO, for example, the most you will get in the best NEO is like 10 people for that sort of amount of time. So, from a first self-sustainable settlement perspective, I think the moon is the obvious place. But turning our attention towards the economics of it, and I'm not an economist, but the thing that leaps out to me from the perspective of this water as a valuable resource there is transportation, and I can see in the long term the moon becoming the ultimate transportation hub for the solar system. You have sort of rail guns along the moon, which to accelerate you off and back, and then you refuel there for your spaceship gets to its destination fully fueled from water being split into hydrogen and oxygen. The only question then is how do we get from here to there? You know, how do we get to that sort of that economic base? And perhaps one thing is sending some of these resources into to satellites that are in orbit. But then the question is, how do we do that? So that was my main question: is like, how do we get small amounts of it to satellites that are in orbit as a near-term step towards the longer-term transportation hub for people?
Great thoughts.
Well, obviously, if you're gonna start creating propellant depots and using lunar water, you're gonna have to launch it off the surface of the moon with rockets, and that's the obvious first step. Until you can build some kind of a ballistic launcher or a mass driver or something like that to get the stuff off the moon, you're gonna have to pay that delta V penalty, which is about 2.5 kilometers per second. It turns out that you can lift with a conventional RL-10 rocket, you can lift about a third of the mass it takes of the whole vehicle to L1, Earth Moon L1, and so you can start depoting fuel right there.
Yeah, people always get very excited about the mass transportation options, but you know, you paddle across the river before you build the bridge, and the problem with the early markets of mass of volatiles delivered back to either a Lagrange point or LEO is that nobody's going to redesign the satellites to accept that propellant until after the propellant supply is there. There has to be an initial investment in infrastructure, you know, to build the depots and start filling them from Earth before other people can take advantage of them. It is the classic transportation infrastructure problem. And you know, I, as no big fan of government in general, recognize that as a legitimate function of government to invest in that kind of basic transportation infrastructure that everyone can use. And I think an exploration mission or something like that that establishes the depot infrastructure is going to have to happen before all those other things are going to happen. Otherwise, we're going to wait a long time.
Okay, Greg.
I just want to kind of say that it's interesting to talk about all this stuff. We have a little bit of work to do before we get there. Like a mining method that's going to work on the moon in partial gravity environments is a pretty hairy thing today with the cost numbers that are going to be able to do this. And from what I've seen so far, there's absolutely no research going on in how to figure that out. You know, I know Leslie and I put one paper into the National Science Foundation about using a method called block mining on the moon. But block cave mining uses gravity. And for what we do today, it's the cheapest way to do it. But the problem is that you're in 1/6 gravity, and there's a lot of problems with trying to sort out how to build a mine like that. And you know, we got to figure all that out before we can worry about mass transportation options and even getting things up into orbit. And I think that there's a lot of work to do yet.
John.
If you think about a model for the deposition of ice in the polar regions of the moon, it involves filling up a pore space by water vapor that strikes very cold minerals. So what you have there is, however water rich, however ice rich it is, it's permafrost. And I once asked an expert at the Army Cold Region Research Laboratory in Hanover, New Hampshire, what I should do if I wanted to mine permafrost. And his answer was, want something else.
Great. Okay, we're going to try and speed the questions up, but on the other hand, it's all really interesting, so go ahead.
I'll speed up. I'm John Cumbers. I'm one of the co-chairs of the synthetic biology meeting.
Can you use the microphone?
Yeah, I think, yeah.
I'm John Cumbers. I'm one of the co-chairs of the synthetic biology meeting, which is also happening at Ames this weekend, and we're bringing the two meetings together tomorrow evening, so I'm very happy about that. And I'm also very happy, Esther, that you brought up synthetic biology, as it didn't give me a need to do so. But the question I have is thinking about synthetic biology and astrobiology. The mantra for astrobiology for the last 20 years has been follow the water. And a lot of you said water's the first thing that we go after, not because we really want it, but because it's the first easy thing that we can obtain. The meeting that we're having this weekend... Well, the reason biology wants it, part of the reason we're having this meeting this weekend is because biology needs it as well. So I think you're going to hear from Craig Venner tomorrow. One of his quotes is, over the next 20 years, everything is going to be made from synthetic genomics. So I think you're going to see the demand for water increase a lot and see biology in space not just as a science, but as a way to do resource utilization. So the question is, shouldn't you consider biology as a way to do resource extraction?
The answer is yes. And that's why we're all meeting together. I think it's great. Yeah.
One quick comment in that regard. One thing that's not mentioned, and the L-Cross papers discussed this at length that just came out last week, is there's quite a bit of simple organic material in the polar volatiles. And the moon, preserving this record, which presumably from cometary sources, actually is a very good source for early prebiotic organic chemistry as a process, is a great laboratory to study that. So I think it's going to really open up new dimensions for astrobiology just by being able to study the polar volatile deposits.
I want to make one very quick comment. I forgot to make it earlier that reminds me of. As far as supporting human populations on the moon, it's been clear to me for 30 years that the rate-limiting element was going to be carbon and nitrogen, not hydrogen. And so the importance of that in there being other volatiles in the poles, I mean, we've speculated that there might be things like methane trapped in there for a long time, but now we have, evidence. So it's looking very, very good, at least for being able to support enough population to run a real mining operation. Whether it has scalability for that other things or not, I don't know. But the press is all excited about the water. I'm really psyched about the methane.
There's carbon and water all over the asteroid belt, probably on the moons of Mars. There's carbon and water everywhere. One word, nitrogen.
Wayne White, author of Mining Law and Outer Space, Space Studies Institute, published it in the early 90s. I was at a Space Resources Roundtable meeting at the Colorado School of Mines a few years ago. We're talking about the same topic. And a guy jumped up in the audience and he says, I work in the oil and gas industry and my company does mining and we have to repair mining equipment all the time. Lunar dust is very abrasive. How are we going to get around that problem if we mine on asteroids or on the moon or Phobos or wherever?
Good question. Greg.
Mining equipment fails all the time because we don't build it properly. So I would argue today that having bought and be one of the person who bought mining equipment for a long part of my life, that mining equipment is built to fail. There are consumables in it, and we do have to deal with the abrasive nature of a few things like drilling holes in rock and picking up stuff that's out there. But in terms of dust and all those things, a lot of things can be done that just haven't been done. And I think that, I've been building mining equipment all my life, and one of the things that was absolutely a no-no was putting hydraulic equipment into a mine because of the dust and dangers of all that. We built the first automatic guided vehicle that was a completely hydraulic vehicle to work in mining, and it amazed everybody. And so there is not yet another hydraulic vehicle like that in existence. And so I would argue that a lot of the people that you probably talked to about that didn't look at what really could be done.
John?
If you're concerned at all about abrasion, and I am for many kinds of equipment, especially mobile equipment, then you really ought to think twice about helium-3, because there you have to handle 100 million tons of abrasive for every ton of helium-3. Sure, it's very valuable, but you've got a big, big problem there.
The only thing I want to add to that is completely agree about with proper design, it can be handled. People have made things that do work in open pit coal mines, and if you want to talk about abrasive environments, whew, they get spooky. The other thing is, bear in mind that for lunar polar volatiles, they're only there because the crater is damn cold. So there may be, because it's also in a vacuum, essentially non-contact-free ways of getting the volatiles out. And some papers have been published on that. They may not, the recovery fraction is lower, but if the equipment's 1% of the mass, who cares? So there's avenues out there to explore.
Okay, next question from Paul Breed.
Okay. Everybody here is a space fanatic or some sort, or you wouldn't be here. This is not necessarily true of the population in general. How do you kick all this off? And my comment is this: we as Americans have like 5% of the population and burn 40% of the resources in the world. We cannot bring the rest of the world up to our standard of living with the resources on planet without having a huge environmental cost. Why aren't we selling space exploration and resource extraction from space as green and as providing the wealth to bring the rest of the world up to our standard of living as a political thing? And just comments from the group.
Two questions. Why aren't we selling it that way, and why or why not will we be successful if we try to do so?
Because this is actually a topic near and dear to my heart, and that is the idea of selling the space program. And it's been debated and discussed for years. NASA's always assumed they have to get people excited. If the people are not excited, they won't support the space program. But I look at it a little bit differently. My position is that if you look at polling data on do you support the space program or not, and NASA has 50 years of this data, Gallup has asked the same question for 50 years, it always comes down 47-53 support, 53-47 against, 55-4, 45 against. It always hovers around 50-50. Now, what I take from this is just the math. What I take from this is that fundamentally the vast bulk of people are indifferent to space. They're not against it, but they're not enthused about it either. They just don't care. And in effect, what they really ask of NASA are two things. One, don't spend too much, and two, don't kill too many people too often. That's really all they want from the space program. If they're doing things that are perceived to be useful and good, then they'll get long-term support. So to answer your question directly, I don't know that you have to convince everyone that we're going to improve life on Earth. All you really have to do is come up with a plan that's clever enough to fit within a certain budgetary envelope, and I think that's the current one, which is about 0.5% of the discretionary budget. And as long as you structure your program cleverly around that, you won't get a lot of flack again. You will be able to start something.
John Lewis and Jeff, and then I'm actually going to comment.
What really engages people's interest is being able to picture themselves up there. They want to see exploration. They want to see new things done. They do not want to see 120 taxi flights to low Earth orbit with people doing the same thing over and over again. That has no great value. Also, the same polls that Paul's alluding to show that the majority of the people in the United States think that the NASA's budget is at least as high as the Defense Department budget.
Jeff?
Space enthusiasts have been bitching and moaning for 40 years that the American public spends more on bubble gum and shoes than they spend on the space program. And we play the world's tiniest violin about, oh, isn't that awful? Okay, there's two things you can do about that. You can continue to bemoan reality, or you can turn the question around and realize that if you could just figure out how to sell bubble gum, you'd have more money than the space program. Things that make money get done whether they're popular or not. Worry about how to make it make money, not worry about how to make it popular.
John, briefly.
Our governing paradigm should not be how are we going to spend taxpayers' donations, but how can we generate business that will pay taxes to the government?
Thank you. Yeah. I just want to say two things on this topic. One is that I don't think people are indifferent. I think, you know, at the top end, you have a bunch of people who are really enthusiastic, who, as John says, want to see themselves up there. There are a lot of people who do not want to see themselves up there, and they are very much against the program. So I think there may be some indifference in the middle, but I would say it's more polarized than indifferent. The second is, unfortunately, what most people want out of NASA, at least in Congress, is jobs in their own district. And that is, I mean, this whole government space program has been so corrupted into fundamentally a jobs program and a political issue that the only way it's going to happen, I think, is if we rely on the private sector. Now, you have a comment on this, right?
Yeah.
Okay, just briefly, and then we'll go to...
Greetings. My name is Ari Novak. I'm with the Oracle Film Group. I'm not an expert in science or mathematics. What I am an expert in is people. And I believe that to be really successful, it's not about a clever way to get around policy or this or that, but you do need to ignite people. This is completely inaccessible to most of the population. But most of the population is totally into this, and our numbers prove that. Look at Avatar. It was a worldwide sensation. And I'm standing here today with the mandate to make the world's biggest documentary, that we can do this. This isn't a dream. This isn't something we can't achieve. It's something we can do. And we can do it if we can ignite that fire with the people. We can't do it if people think it's not important to them, if it's something they just look up to the sky and it's far away. If it's completely inaccessible, I don't believe it'll ever be done, even if it can make money, because it seems like you can't touch it. If you can touch it and make it real, and you can ignite the fire in the people, it will be. And that's why I'm here, and I'm thrilled to. Thank you.
So do you have funding for this documentary? Yes, I do. Let's talk later.
Gary Barnhart. Listening to this, you know, it comes down to, you know, we're sort of the pragmatic twist. I was hearing all the different pieces. And one of the things that first struck me, this notion of economic analogs or models, it seems like we're actually closer to the chop shop model, if you will. What we love to be able to do is take a very small chunk of an asteroid or a near-Earth object, move it to a minimum energy location that's convenient from a delta V standpoint in cislunar space, not so close that we get the lawyers upset, okay, but not so far that it's a problem, and you know, part the damn thing out. Split it into every conceivable component that somebody might find some value in, and figure out how to do that. And you start small, okay? But then you've got a set of pieces, and in so doing, you're leveraging both the research community, the technology development community, and you stand a reasonable chance that we're going to figure out ways to make some money on the pieces.
Any reactions?
When you know how to do that, go look for funding.
Okay, so it's now 8 o'clock, and what I'd like to do is have the 4 questions at the same, one after the other, but just all 4 of them together, and then have the panelists react to the 4, you know, pick the one you like, take them all, whatever, but we're going to try and kind of do a glorious wrap-up, because I think everybody wants to go either get a drink at the bar or come talk to some of our panelists.
Continue the discussion at the bar.
So if you guys all come up, we'll just do all 4 of you almost together.
I'll try to keep it brief. My name is Gary Miloglov. I have a question mostly about economics, politics, and mining. China has rare earth elements, 80% of them. Are there enough rare earth elements, and they've stopped exporting them, so this is a big problem. Is there enough rare earth elements on the moon or in asteroids that could make it feasible to bring it down here, or should we be developing the mines on Earth?
Can I respond? There's enough on the Earth.
Okay. There's enough on the Earth.
But not being exploited.
That's a temporary situation. That's not because of a scarcity.
We hope. And I guess it can be addressed by mining elsewhere if necessary.
They stopped the embargo of China's exporting as
Yeah.
for China.
Okay.
I'm Mark Hopkins with the National Space Society. And my question is, what is the optimal mix for, say, lunar development of government versus private enterprise? I mean, there's some people that believe that you really need a large government program to go to the moon before you can really do much private enterprise. There's other people that think that the best thing you can do is keep the government out of it entirely. So what's the mix?
Great. So we're going to save that question up. Next one.
Hi, I'm Silvano Colombano from NASA Ames. In terms of motivating the people, I'm surprised that the idea of space defense from asteroids hasn't been brought up. That could be a major motivator. Fear always is a motivator. In this case, the fear is real and legitimate. The question that I have, can planetary defense be connected also with the possibility of commercialization? I'm not clear how that could be happening.
Okay.
Phil Chapman again. My first ancestors arrived in Australia in 1800, and I think there is some useful analogies between the settlement of Australia and the settlement of the solar system. In the first place, it was a one-way trip. People who went to Australia from England knew that they were not coming back, almost all of them. Some of them were involuntary. They were convicts. My first ancestor in Australia was a convict, which in Australia is like having somebody who came over on the Mayflower in the United States. but the thing about the Australian, the reason for it was that the pesky colonials in the Americas had shut down the prison colonies, and they needed somewhere to, the English needed somewhere to send their prisoners. So they had a motivation which lasted for maybe 30 years or so, but in that time there was a sufficient interest developed in farming and turned into a society, and it took off. So what I think we need in space is a similar motivation which leads to getting the critical mass together that makes settling the rest of the solar system inevitable. And I would suggest, and I will try and make the case on Sunday, that the answer to that is the solar power satellite. If only because any kind of solar power satellite program that is at all meaningful means that we have to launch at least 100,000 tons a year into orbit. And if we're doing that, we're going to be talking about, just with current rockets, if they're merely reusable, we just go to reusable rockets, we can get the cost of launch down to about $300 a kilo. And that makes a great difference to what we can do.
Thank you. My ancestors came to the U.S. and went back to England, but it's another story.
David Beeler. Question for the panel. If you look at, we've got rocket engines, we've got mining equipment. This technology has been around for 30 years at least. Yet not a single ounce of asteroid has been brought back, either for mining or science. So if you look, there must be some obstacles in the way, obviously. So if we look at these obstacles, what are the weak links in the obstacles? If we're going to remove these obstacles or overcome an obstacle, can we overcome it with the technology? Can we overcome it with political will, with private equity, motivation? What does the panel see as a weak link in the obstacles preventing asteroid mining or any space resource extraction?
Thanks. That's a very good question to finish up on. So what I'd like to do now is simply go back in. This time I won't follow the paper. I'll just go this way, starting with Dr. Spudis. Just you all have a chance to react to any of those questions or none of them and come up with your own. But this is your last word.
Okay. In regard to the last question, how do you get started? I think a big problem is a lot of people in the space business don't really believe this is possible. They don't believe space resources and space resource extraction and utilization can be done. They think it's flaky, they think it's science fiction, they don't want to hear about it. And most of these people are in decision-making positions in both NASA and in the United States aerospace industry. So that's why it hasn't been done. You need to somehow make some kind of a demonstration to show it is possible for this to become not laughable. That's one point. The other point is how, someone asked the optimum mix of private sector and government. I think the optimum mix was provided by the now discarded vision for space exploration, whose fundamental mission was to go back to the moon to learn how to live and work on the moon. And that was the mission of the vision. And effectively, if you were to do that, resource extraction and utilization is part of that. If you're going to live on another world, you need to extract and use what you find there. So that was a good way to do it. The government goes, it demonstrates that this is possible, it demonstrates some of the technologies you need to do it, and then it passes it on. So that, to my mind, that's the way to start the mix, is you let the government lead the way and then let the private sector follow.
Thank you. Jeff.
The reason neo mining isn't happening is because nobody's figured out a way to make the business case close. And I don't think that that's going to be solved anytime soon. The reason why moon mining isn't happening is because the critical early demonstration market, which is propellant, has to have that market primed. The return on investment for that will not happen soon enough for it to be a private sector investment. So that's an area where an appropriate government investment can catalyze it. And that goes to the question of what's the appropriate public and private mix. It is a legitimate purpose of government to make investments in infrastructure and technology demonstration where the future economic value of that investment is huge, but where it doesn't necessarily come back to the people making the investment. You know, the highways were not a profit-making enterprise, but it's a good thing we have them. But if we expect government to lead the way in showing how to cost-effectively extract, use, and transport resources, we expect what never was and never will be. So the optimum mix of government and private is the government shows the initial demand and the private sector figures out how to provide the supply.
Thank you. John Lewis.
My mother's ancestors came over to New Amsterdam in the 1620s and 1630s, and what they did is they signed a contract with a company, the Geachtreide West-Indische Company, okay? The Dutch West Indies Company. They signed a contract that they would go there and work for the company, and after 10 years, they would get free transportation back to the Netherlands. None of them wanted to go back to the Netherlands. They were mostly religious refugees. They were French Huguenots. They were Dutch. They were English. They wanted to be here. So when their contract expired, they picked up and moved a few miles and started their own farms. Eventually, New Amsterdam became so lucrative that the British government decided they wanted it, and in 1672 they took it over. A warning.
Thank you. Okay, Mark, one more thing.
He says that Viva the Revolution in space. At the time of the American Revolution, there were an awful lot of people from New Netherlands who never thought the British were a very good idea.
The moon is a harsh mistress.
Mark.
I'm going to refrain from talking about my ancestors coming out to Australia in 1836 and then being found 10 years later squatting 15 kilometres out of Sydney in the bush where the tax man never went. But Phil Chapman raised solar power satellites, and you need some such large economic driver to get us over this critical mass. I agree.
Okay, Greg.
I'd like to take a stab at the question of government versus and how much should be in each one. I got all my experience in a big ore body in Sudbury that ultimately economically has a value of in the order of $2 or $3 billion. To start it was started by the military, and the military happened to need replacement for the sides of the old Ironsides battleship. And one of the executives of Inco at the time, which was really only 4 guys, figured out how to make stainless steel plates and took them down to Washington, and somebody fired cannonballs at them and realized they weren't going to work hard, and the old Ironsides weren't going to go down at the same rate as whoever you guys were fighting at the time. I'm not good at this history down here. But the reality is that, was it a war with Canada? No, I don't think it was. No. It was the British probably, right? Anyways, at the time, the military got quite involved in it. And I know as we're doing this project that we're in the James Bay Lowlands, we're even looking to government support because the infrastructure requirements for even setting up this mine are a requirement. And so the government has to work in partnership with the private sector to make some of these things happen. I would also argue, after being involved in the Long Now work that I've done, that a lot of the economic values, when they start exceeding 10 years or 15 years, start becoming more societal problems. And so you want to take a look at how government and business are going to interact on 100 and 1,000-year time frames, because they have all the way through and they will into the future. So I think it's got to be a mix of all those things together. And to think it's just going to go to the private sector, I don't think is right.
Thank you. Mike Ahern?
Let me address 2 points. First off, the question was raised, why hasn't any mining been demonstrated to bring back a sample from an NEO, and why haven't we actually done any even for science? So let me just comment on the science drivers. First off, many kinds of asteroids, the samples are already here. We call them meteorites. And we don't have to go get them. Nevertheless, it is clear from all of the activity in NASA that NASA is moving to sample return, over a wide range of activities. And I will wager, we have had samples back from one comet, a microgram or so. Maybe it was a nanogram. I wager that we will have samples back from either an asteroid or a comet within 20 years for research purposes. It's clear that all of the mission studies that are going in, that'll happen. Somebody else raised the question of the NEO hazard to the Earth and how that plays into this. It does play into it because all of the techniques that you need to think of to save the Earth from being hit can equally well be applied to delivering things to the Earth. There's a concept called the gravity tractor. I was at a meeting in Russia last year where one of the Russian scientists said, the first thing we have to do to improve the ability to defend ourselves against NEOs is to outlaw the gravity tractor, because the gravity tractor is so precise it's too easy to make it into a weapon. But instead, we should revoke the Treaty on the Peaceful Uses of Outer Space and the Nuclear Weapons in Space Treaty, so that we can test nuclear weapons to deflect them. So there's a wide range of ideas on how we should be approaching this. But it is the case that the same techniques that you use to save the Earth are relevant to bringing things to the Earth to work with them.
Okay. I want to thank Lee for organizing this in the first place. I want to thank the excellent panelists. And on behalf of all the synthetic biologists, I want to say what a great evening it was hearing from you mining guys, and I think we're all looking forward to a wonderful weekend, both separately and together. So thank you all very much, and the bar is open.
panel on